All right, chemistry, let's take a look at our video lecture for chapter 11, section 3. In this video, you will not be spending a lot of time taking notes because while it is true that we have an entire section dedicated to stoichiometry of gases, you already know quite a bit about stoichiometry and quite a bit about gases. And so, all we're doing in this lecture is putting the two topics together. You already know how to do stoichiometry, and you already know how to do calculations using the gas laws. Now we're just going to put them together. So after this video, I want you to be able to explain how Gay-Lussac's law and Avogadro's law apply to the volumes of gases in chemical reactions. Right now we're looking at reactions, stoichiometry. Then use a chemical equation to specify volume ratios for gaseous reactants or products, or both. Okay, this is something that we already took a look at when we were going over Gay-Lussac's law of combining volumes. Now we're just going to apply that to stoichiometry, leading right into our next objective. Use the volume ratios and the gas laws to calculate volumes, masses, or molar amounts of gaseous reactants or products. Now, we're only doing this with gases. Remember that these laws only apply to gases. That's why we're using volumes. But here we go. So we're doing gas stoichiometry. Gay-Lussac's law of combining volumes of gases and Avogadro's law can be applied in calculating the stoichiometry of reactions involving gases. Right? So we have Gay-Lussac's law of combining volumes, and we have Avogadro's law, which is the mathematical relationship between volume and number of moles. We know standard molar volume. So at STP, 1 mole of any gas occupies 22.4 liters. Right? So we're using those two ideas to lay into stoichiometry. The coefficients in chemical equations of gas reactions reflect not only the molar ratios, but also the volume ratios. Again, assuming conditions remain the same. So pressure and temperature must be held constant, which is the same as when we were going over Gay-Lussac's law of combining volumes and Avogadro's law. Temperature and pressure had to remain constant. So that's still the case here, still the case. But as long as those conditions are met, the coefficients in a balanced chemical equation represent mole ratios, like we've already done in chapter 9 when we introduced stoichiometry, but they also represent volume ratios, like we introduced in section 1 of this chapter, right? Gay-Lussac's law of combining volumes. So, for example, if we have carbon dioxide gas reacting with oxygen gas to form carbon dioxide gas, right? Notice they're all in the gaseous phase. We see that the coefficients of that balanced chemical equation are 2, 1, 2. So we get lots of information out of this. We know that it takes 2 molecules of CO to react with 1 molecule of O2 to yield 2 molecules of CO2. At the same time and in the same way, 2 moles of CO react with 1 mole of O2 to yield 2 moles of CO2. What we're extending here with the gases in chapter 11 is that 2 volumes of CO react with 1 volume of O2 to yield 2 volumes of CO2. And so we can use this relationship of Gay-Lussac's law and Gay-Lussac's law of combining volumes and Avogadro's law to step into stoichiometric calculations. So you can use volume ratios as conversion factors in gas stoichiometry problems in the exact same way you would mole ratios. Now, and we can invert them as well. We can specialize them to deal with whatever units we want to cancel out and whatever units we want to move into, right? And we can flip them. We can invert them depending on what we want. So we can write 2 volumes of CO to 1 volume of O2, or 1 volume of O2 to 2 volumes of CO, right? We can invert that. We also have the another version, 2 volumes of CO yield 2 volumes of CO2, and you can flip that. You can invert it as well, and on and on and on, in the exact same way that we introduced mole ratios in chapter 9.
Gay-Lussac's law of combining volumes of gases says that gaseous products and reactants have ratios that can be expressed as small whole numbers. So if, at a constant temperature and pressure, one volume of hydrogen gas reacts completely with one volume of chlorine gas to produce 2 volumes of hydrogen chloride gas, we know that the mole ratio of the reactants is 1 to 1.
So Robot Lady was correct, but that video wasn't very smooth. So, but let's look at a sample problem. What are you going to have to do with this information? What are you going to have to do with this information? There's a sample problem. Propane, which is C3H8, is a gas that is sometimes used as a fuel for cooking and heating. You guys have heard of propane. The complete combustion of propane gas, right? And you guys know what combustion is. Occurs according to the following balanced equation. Oh, how nice of us. We're actually giving you the balanced chemical equation. First question, A. What will be the volume in liters of oxygen required for the complete combustion of 0.350 liters of propane? Second question, B. What will be the volume of carbon dioxide produced in the reaction? Assume that all volume measurements are made at the same temperature and pressure. Again, temperature and pressure have to be the same in order for Avogadro's law and Gibbs-Sachs law of combining volumes to apply. Well, let's take a look at how we're actually going to do this. Right? We know for part A, we know that we have the volume of the propane gas. It's 0.350 liters. We also have the balanced chemical equation. Right? So that's super important. What we're trying to find here is the volume of O2. Right? So it's still going to be in liters, but it's going to be in liters of O2. The idea here is that because all volumes are to be compared at same conditions, the volume ratios, right, the fact that all the conditions are the same, allow the volume ratios to be used just like mole ratios. And so I start with that value that I'm given, the 0.350 liters of propane, and I cancel out of liters of propane and convert into liters of O2 using the coefficient, the ratio, the volume ratio of 5 to 1. 5 volumes of O2 to 1 volume of propane. Simple calculation into your calculator, 0.350 multiplied by 5 divided by 1. Your final answer is 1.75 liters of O2. Part B, again, we have the balanced chemical equation and we have the volume of propane, but this time we're trying to find the volume of CO2. And again, we're using the same conditions, same temperature and pressure, that allows us to use the volume ratios in the exact same way that we would use mole ratios. So, yet another conversion factor, that is a liter to liter, a volume to volume ratio. I have my 0.350 liters of propane multiplying by a conversion factor, which is 3 liters of CO2 to 1 liter of propane, right? Because the volume of CO2 to propane is 3 to 1. Again, based on the balanced chemical equation, final answer is 1.05 liters of CO2. And that is it for section 3.